Started. So we
Okay.
want to welcome our speaker today, Professor Mochalin from Missouri University of Science and Technology. He is going to be speaking to us about Chemist's adventures in Nanomaterials Wonderworld. So I guess we'll find out all about what that means. It sounds mysterious. He has co-authored 60 research papers, written several book chapters and review articles. He's an inventor on about 6 international patents. His area of research, I'm pretty sure, is what his topic is going to focus on here today. In terms of educational background, he comes to us from what I could see, the Ukraine, a PhD in physical chemistry, and prior to that, a bachelor's and master's from Donetsk National University in Ukraine. Okay? But right now, again, as I said, he is at the Missouri University of Science and Technology. So it's a pleasure to welcome you to our seminar series. This is a special year for us. It's our 50th year in terms of the seminar program and 75th year for the department. So it's a double anniversary that we're having. Again, welcome you and look forward to your presentation.
Okay. Thank you very much. Let me first start with thanking you for inviting me to be part of this long lecture series and the Feast of Chemistry. I've seen how many excellent speakers you already have before me. So it's really an honor for me to be in a good company and again celebrate with you this special year. So the topic of my talk today is 210 Chemist's Adventures in Nanomaterials Wonderland. You will see what 210 means, but I have background in chemistry. I worked for a number of years in material science, so I had an opportunity to look at the same things from the two different standpoints. And I will try to exchange my experience with you today. First of all, let me acknowledge help of the students who contributed to this work. So those are people who did the work. They worked with me at Drexel University when I was still at Drexel. I just started at Missouri S&T about 4 months ago. So I'm still new here. Also, help which I received over the years from my multiple collaborators. And those are, I believe, some of the excellent, some of the best researchers in their fields. I collaborate with people basically all around the world, of course, in America, Drexel University, Oak Ridge National Lab, University of California, Los Angeles. I also collaborate with people in China, in Ukraine, in Israel, Germany, France, and this is not the full list, but just to give you an idea that nowadays research cannot be done individually, or very little can be done individually. So good research is normally done nowadays through collaboration. And again, I was blessed to have some of the most excellent people collaborating with over the past 10 years of my career. Let me start with a little bit of introduction of myself and my work and my experience. So basically my research is related to nanomaterials. And I worked with all possible nanomaterials starting from 0D through 1D to 2D nanomaterials. As you will see later, any nanomaterial has to be either 1D, 0D, or 2D. When it's 3D, it's not nanomaterial, it's bulk material. So 0, 1, 2 means different dimensions of nanomaterials. And as you can see from this short list of my papers, I worked with 0D materials, which is nanodiamond. I worked with 1D nanomaterials. Those are better known to general public, carbon nanotubes. nanowires, things like this. I also work with carbon nanoscrolls, which are in between 1D and 2D materials. And over the past few years, I work extensively on 2D nanomaterials. And those include, of course, graphene, which everybody knows now. But we also discovered new large family of materials, MAXenes, when I was at Drexel. And I also work with boron nitride. And I also do computational modeling of materials. And these are some journals where I published my research. And now for about 3 years, or more actually than 3 years, I work on the editorial board of Scientific Reports, which is published by Nature Publishing Group. So it's open access journal, which publishes basically research from all possible areas of science. It has no certain focus. So some of the cover images which resulted from my work. These again give you a good feeling of different nanomaterials I worked with. On the left, you see there is silicon carbide in the background, graphene sheet, there is carbon onion structure here in the lower right corner, and multi-wall carbon nanotube. And there is amorphous carbon here in the background in the in the right top corner. On the right image, it's a structure of MAXene, computer model, basically blended with scanning electron microscopy image of MAXene, which was on the cover page of Advanced Materials, where we published in 2014 first review on this large family of nanomaterials, which I'm going to talk about later. But first of all, let me again share with you some experience which I got by working with chemists and material scientists, basically how they see same things. So a material versus a chemical. First of all, how chemists see the world? Well, for chemists, everything is chemical substance, right? And chemical substance has a definition in Gold Book, EUPAC Gold Book, which you can go to this website and find this definition. That's it's a matter of constant composition, best characterized by the entities, molecules, formula unit, atoms. And a material, if you will try to find a definition of a material, you will see that actually there are many definitions of material. There is not one, which tells you immediately that it's more difficult to define the material. But basically, most important difference between a substance and the material is this constant composition of a substance. So constant composition is a definitive characteristic of chemical substance. And that composition, constant composition, is reflected by chemical formula. This is why when, for example, sometimes you hear people working in nanotechnology, they discuss things like this. Look, our nanoparticles got so small in size, maybe we should think about them as molecules now. And as a chemist, you always raise your hand and say, no, you should not, because a molecule must have constant composition. And your nanoparticles, no matter how small they are, until they have constant composition, they cannot be considered as molecules, okay? And from that standpoint, for example, C60 is a molecule, because it always has fixed composition, C60. But for example, gold nanoparticles, carbon nanoparticles, diamond nanoparticles, no matter how small they are, if they do not have constant composition, they cannot be considered as molecules. So this is what chemistry taught me, and this is what material scientists consider kind of differently and pay less attention, although they should pay more attention to that. But on the other hand, there is something which chemists can also learn from material science. And for me, that was, for example, the concept of dimensionality of materials, which is not that common in chemistry, but is very common in material science. So depending on dimensionality, materials can be classified as 3D, 2D, 1D, 0D. Again, if you go to EUPAC website and will try to find a definition of nanomaterial, it will be difficult to find it. But EUPAC defines nanocomposite, okay, and the definition is listed here. What about nanomaterials? Well, I only found definition of nanomaterials on Wikipedia website, and that definition basically tells that nanomaterials describe in principle materials for which a single unit is sized in at least one dimension between 1 and 1,000 nanometers. Okay, so it's 10 to the minus 9 meters. Okay, and usually this dimension should be between 1 and 100 nanometers. So you see the definition is less precise compared to the definition of chemical substance. But again, we have to use what we have. And using this definition, we can classify all materials as 3D in case when all dimensions are more than 100 nanometer, 2D when one dimension is less than 100 nanometer and other two dimensions are more, 1D when two dimensions are less than 100 nanometer, and 0D when all dimensions are less than 100 nanometer. So for the purpose of this presentation, I will be focusing basically on 0D and 2D materials. Now, why anybody would care about dimensionality of materials besides purely geometry? Okay, so 2D materials have one dimension less than 100 nanometer, and what? It's just geometry. So why it would be important for us as chemists, as material scientists? Well, it turns out that dimensionality actually dictates many properties of materials. And in particular, what I show here, electronic density of states strongly depends on dimensionality. So for the material of the same composition, but having different dimensionality, you see how dramatic the changes are in electronic density of states, where we go, for example, from 3D bulk material to 0D quantum dot. Okay, you see that the electronic density of states changes completely. We are not talking about differences as in like 2 times, 5 times. The shape of this function completely changes. So the effects are dramatic. Now, if electronic density of states changes, then basically all electronic and optical properties change. Okay. Same happens to, say, vibrational density of states. It also changes depending on dimensionality. And changes in vibrational density of states result in changes in thermodynamic properties. Heat capacity and other thermodynamic properties changes. So eventually, even stability of this material depends on their dimensionality. So you should pay actually a lot of attention to dimensionality of materials. And this is what I learned from material science as a chemist. Chemists should pay more attention to dimensionality of their molecules, especially when they're talking about very large molecules and materials, of course. Now, let me switch now to one of the materials I work with, which is nanodiamond. Nanodiamond is 0D material, which means all dimensions are less than 100 nanometer. Now, again, when I talk to material scientists, this is how basically students in material science are taught about different carbon materials. They normally would be shown this diagram of different carbon allotropes. And from this diagram, you can see that carbon actually has a lot of different forms. 3 main forms are related to 3 main hybridizations in carbon, and that is sp3, which gives rise to diamond, sp2 to graphite, sp to carbene. Carbene was not experimentally observed yet. But what is unique about carbon is that it can also form all possible intermediate forms. Say between sp3 and sp2, there are a lot of different other hybridization states of carbon which give rise to different materials. So for example, fullerene is between sp3 and sp2 carbon. Okay, and this is what makes this element, I mean carbon, so versatile. This is what makes it so ubiquitous in our lives, because carbon can form many different materials. Again, we are going to talk about nanodiamond, so it belongs to this part of the triangle. It's basically diamond structure, carbon in sp3 hybridization form. Chemists normally think about it a little bit differently. And when I teach chemists, for example, on nanodiamond, I usually start with methane. So it's the simplest sp3 hybridized carbon molecule in which you have carbon connected to 4 hydrogen atoms. Now, you can build all varieties of different sp3 carbons starting from methane, at least theoretically. There are different ways to do it. One way is to say, okay, I just take this hydrogen atom on the right and replace it with another carbon atom. Then I take the hydrogen atom attached to that carbon atom and replace it with another carbon atom. And I do this in just one dimension. So preferentially, it grows in one dimension. By doing this, you go from methane through N-alkanes, and you eventually can produce large polymer chains, which are materials. But you can do it also in a different way. You can say, okay, I can also more or less uniformly replace all 4 hydrogen atoms by carbons in 3 dimensions, okay? And if you do it this way, then you go from methane through diamondoids. Those are still molecules. They have fixed compositions, and they were recently discovered in oil. So they exist. They were characterized, isolated. And if you keep doing this, you can increase the size of diamondoids. If you keep doing this, you will eventually come to diamond, bulk diamond. Well, bulk diamond is anything which is larger than nanodiamond. So basically, microcrystalline diamond in this representation is also considered as bulk diamond. And between the diamondoids, which have this characteristic size, and bulk diamond, which has this characteristic size, you have basically nanodiamonds, okay? So this is how chemists are introduced to nanodiamond. Now, why we are interested in nanodiamond? Well, because it's essentially diamond, but at the very, very small scale. And diamond has some very unique properties. I would say it has extreme properties. And what I mean by extreme, it means that it has either extremely high or extremely low properties, basically for each property you can think of. For example, Young's modulus is very high, hardness is extremely high, but friction coefficient of diamond is extremely low. Density is high, thermal conductivity is high, but for example, thermal expansion coefficient is extremely low. So whenever you look, wherever you look, diamond is usually at the extremes of the ranges of possible values for pretty much any property you can think about. This is what makes this material special and unique, its extreme properties. The material I'm going to talk about in this talk is a nanodiamond produced by detonation. Let me first say a few words about this synthesis technique. So nowadays there are many techniques to produce diamond, and nanodiamond also. In particular, nanodiamond can be produced by CVD techniques, can be also produced by high pressure, high temperature techniques, but one of the most, one of the simplest or one of the easiest techniques is detonation synthesis. What it means is you take molecules of explosives, which are organic molecules, and you select them and combine them in such a way that you would have negative oxygen balance in this mix of explosives. What I mean by negative oxygen balance, I mean that you have not enough oxygen in the molecules of these explosives to convert all carbon atoms into carbon oxides. So some carbon atoms will be left in the form of carbon. They will not be oxidized. And you place this mix of explosives in a detonation chamber. Okay, so it's a closed chamber filled with inert atmosphere, nitrogen, argon. Sometimes people even use water. And then you do detonation there. You have very high pressure and temperature, as you can see at this diagram. And the range of pressure and temperature developed during detonation corresponds to the domain of thermodynamic stability of nanodiamonds. So it's this point A here on the phase diagram. So the excess of carbon atoms present in these molecules of explosives starts to form diamond phase. And it starts to grow, but again, detonation is a very short process. Pressure and temperature drop quickly back to normal conditions. So the growth is not prolonged. it stops very quickly after the growth was initiated. And basically, your system moves along this red line from A to comes to the domain of thermodynamic stability of graphite, and then eventually, when temperature drops below 2000, everything stops. So nothing changes, and you have nanodiamond formed. Now, this material is commercially available. Again, when I talk about nanodiamond, or when people first time hear about nanodiamond, they think that, okay, maybe this is something very expensive, exotic stuff, because they know that diamond is expensive. So probably it has no practical applications, just chemists play with it out of curiosity. It's not true. It's true actually for most of nanomaterials, because most of them are difficult to produce or expensive to synthesize. Nanodiamond is a notable exception in this case, because nanodiamond produced by detonation is very cheap material, and it can be produced on a large scale, is available commercially, and you can even go to Sigma Aldrich website and buy it. Okay, of course the price here is much more expensive compared to what you get if you just go to the manufacturer directly, contact the manufacturer and buy this material from the manufacturer. But on average, the price of nanodiamond is comparable to the price of multi-wall carbon nanotubes, which is a few $100s per pound. So it's affordable material even for large-scale commercial applications. The structure of nanodiamond particles is shown here. So on average, they all have approximately spherical shape. The diameter is about 5 nanometer, and it's very uniform. So unlike many other nanomaterials for which you have to do fractionation to separate them in fractions, when you synthesize nanodiamond by detonation, you basically get particles, pretty much 100% of particles with size very narrowly distributed around 5 nanometers. So you get very small particles and very uniform in size, spherical shape. The core of the particles is made of diamond, so this is diamond structure here. And the surface is terminated with many functional groups. Okay, and this black stuff here is sp2 carbon, because the dangling bonds on diamond surface have to be either terminated by heteroatoms forming functional groups, or they will combine with each other and form sp2 carbon on the surface. So this is why any nanodiamond has some amount of sp2 carbon on the surface. Now, if you look closer at the structure of these functional groups, you will see that they are mainly oxygen-containing functional groups, for example, OH, COOH, like shown here. There is also some amount of NO2 groups. Those come from purification procedure, because people normally use nitric acid to remove non-diamond carbon. And this is the structure of sp2 carbon. So again, you can see that sp2 carbon forms patches of polyaromatic structures on the surface of nanodiamond. But again, otherwise, this material behaves as typical diamond, even shows typical for bulk diamond twins. Twins are special kinds of defects which are typical for bulk diamonds. So nanodiamond also shows them. Over the years, when we worked with this material, we learned actually that in order to use this material for any application, one has to pay attention to several things. One of them is functionality, so the chemical nature of those functional groups on the surface. But also one has to pay attention to characterization, purity, and dispersion of this material. Characterization is very important. Again, remember that this is a material, this is not a molecule. So the material which you buy today may be totally different from the material which you buy from the same manufacturer tomorrow. So you always have to characterize it to know what you work with. And here I show for example, 3 different batches of material bought from the same manufacturer, but you see how different they are when we characterize them by Raman spectroscopy and by transmission electron microscopy. For example, in detonation soot, you will not see a peak corresponding to diamond in Raman spectrum at all. So you can easily come to a wrong conclusion that there is no diamond in this material because you don't see diamond peak, and Raman spectroscopy is commonly used to detect different allotropes of carbon. Okay, but then if you put it under transmission electron microscope, you would understand why you don't see diamond peak here, because your diamond core is engulfed by layers of graphitic carbon, and there's a lot of amorphous carbon around. So basically your diamond core is heavily shielded, and you simply cannot see Raman signal from it. Okay, if you purify it, then you get less graphitic carbon, and you can again see it clearly under TM for this material and for this material on top. And then you will start seeing more and more pronounced diamond peak. So everything is okay with the material. It's still nanodiamond. You just need to keep in mind that, again, this is a material, not a molecule, doesn't have fixed composition. So this material has much more non-diamond phase, which you have to remove if you want to work with nanodiamond. And when you remove it, you get all typical signals in Raman spectroscopy and in TM, typical for nanodiamond. Which brings me actually to the next important thing, purification. So first of all, characterization. Whenever you get this material from the manufacturer, characterize it. You need to know what you work with. Then in most cases, purification is required. You need to remove all these non-diamond carbon, which you see here and here, graphitic shells. You need to remove all of this if you want to work with nanodiamond. And there are different purification strategies. Most common is liquid oxidation, which is used by manufacturers. But it's not practical because, again, liquid oxidation uses large amounts of very aggressive stuff like nitric acid, chromium oxide, hydrogen peroxide, chloric acid, perchloric acid. So all those are very aggressive and nasty substances to work with. So we developed in 2006 a technique based using air for oxidation of non-diamond carbon. But there are also other alternatives. You can use ozone, you can use hydrogen. But again, you need to purify it. You need to use the right technique to purify this material to remove non-diamond carbon. And then you can do functionalization, because again, for most applications, you need to functionalize it because you have a lot of things on the surface. And for most applications, this mix is not good. You need to have just one type of functional groups on the surface, then you can get advantages of diamond properties in this application. Now I will show you a few slides about our achievements in all these important directions in nanodiamond research. So here is air purification, which I mentioned before. When you get nanodiamond from detonation reactor, this is how it looks like. So it's black. Why it's black? Because it has a lot of non-diamond carbon. If you put it under transmission electron microscope, you will see that there are diamond particles here and there, but the majority of material is made of non-diamond carbon. Mainly carbon onions shown here, also amorphous carbon here. So all this needs to be removed if you want to work with nanodiamond. We discovered in 2006 that this can be done by simply heating nanodiamond in air atmosphere. So imagine we go from all those aggressive liquids, nitric acid, sulfuric acid, chloric acid, and so on, we completely eliminate them. We just heat material in open air. So the only reagent actually which is used in this technique is just oxygen from air. The key here is that you need to do it at 425. And this temperature is very sensitive, because if you go 10 degrees C above this temperature, then you start oxidize diamond and you lose diamond. And this is not what you want to do, right? If you go lower, 10 degrees C lower than this temperature, nothing happens, you do not purify it. So it was very critical to discover this particular temperature, and then we published this paper in 2006 in Journal of the American Chemical Society, and now this technique is one of the most widely used purification strategies for diamond. And then after purification, you can see immediately visually that the appearance of the material changes, it becomes much lighter compared to this. And if you put it under transmission electron microscope, you will see that the material is mainly made of diamond. There is almost no non-diamond carbon at all. So by using air oxidation, we can go from about 25% of diamond in this material in detonation soot up to 95–97% of diamond. So it's one of the purest nanodiamond I've ever seen. And again, let me remind you that you can never expect 100% of diamond phase in nanodiamond simply because those dangling bonds on the surface have to be either terminated by heteroatoms or combine and form sp2 carbon, which is non-diamond carbon. Okay, so this is one of some of the highest contents of diamond you can expect in nanodiamond. Then we deagglomerate this material. To deagglomerate it, we simply mill it with such things as salt or sugar. You may say that, well, salt or sugar cannot mill diamond because it's much softer compared to diamond, and I agree. But our goal here is not to mill actually diamond particles. Our goal here is to break nanodiamond particles agglomerates, and those are not that strong as diamond, even not that strong as salt or sugar. Okay, and for that purpose, salt and sugar work perfectly fine. And to demonstrate you how they work, I show here, first of all, milling kinetics. So we mill nanodiamond with salt in this case for different amounts of time, shown here. And you can see that we start with nanodiamond which are heavily agglomerated. We have the size of agglomerates is more than 1 micron, this black curve here. And over the milling time, over 5 hours milling time, you can see how this peak goes down and the amount of small particles increases. And eventually we can, with pH adjustment, we can reach almost primary particles. You remember that nanodiamond particles have 5 nanometer in size. So our particle size distribution is peaked below 10 nanometer, at about 7 or so. So those are basically primary particles of nanodiamond. And the advantage of this technique is that we can easily dissolve salt and sugar. After milling, we simply put the material in water, salt and sugar get dissolved, we can wash it with water, and nanodiamond stays in suspension. And this is how they look before milling. So this is what I get when I disperse nanodiamond after purification, air oxidation. But without milling, when I try to disperse it in water, you see the liquid is cloudy. So the size of agglomerates is in micrometer size, micrometer range. And when I do milling and disperse it in water, this is what I get. It's a clear solution. It still has dark brown color. And actually nobody in nanodiamond community still knows why pure nanodiamond and well-dispersed nanodiamond has this dark color, because diamond is transparent, right? So you would expect the suspension to be clear. But it turns out no, and the better you disperse it, the darker is the color. So it's one of these puzzles in nanodiamond community which still waits to be resolved. Next step, after we have our material purified and deagglomerated, we functionalize the surface. So after air oxidation, all variety of those different functional groups is converted into primarily just one type, which is carboxylic group. So we have nanodiamond terminated with carboxylic groups. And then you can pretty much open your organic chemistry book, go to chapter on chemistry of carboxylic groups, and try different reactions typical for carboxylic groups to functionalize nanodiamond. So I just grouped these reactions here in this diagram very schematically. You can use, for example, high temperature gas chemistry, basically anneal this nanodiamond in different gases, ammonia, chlorine, hydrogen. You can even anneal it in vacuum at high temperature. By doing this, you convert nanodiamond into carbon anions. So basically, you convert sp3 material into sp2 material. Or you can use wet chemistry techniques and, for example, reduce carboxyl groups with this reducing agent common in organic chemistry. You'll get hydroxyl terminated nanodiamond. If you treat it with styrene chloride, you can produce acyl chlorides. So it's nothing new. It's basically known chemistry of carboxyl groups. Sorry, wrong direction. Yeah, it's basically known chemistry of carboxyl groups applied to nanodiamond. And then, for example, these acyl chlorides are very reactive, and you can use them for to produce many different products. And in particular, we use them to produce, to attach diamines, as shown here, to produce aminated nanodiamond with amino groups on the surface, and monoamines to produce nanodiamond terminated with long hydrocarbon chains, which is R here. So again, we are not doing anything new in terms of chemistry. All those are known reactions. But it's very new. I mean, it was at that time very new for nanodiamond. So here I show how we produce, for example, aminated nanodiamonds. So we start with carboxylated material, activated with thionyl chloride. We produce acyl chlorides on the surface. Then we reacted acyl chlorides with diamine, ethylene diamine. One amino group reacts with acyl chloride and forms a amide bond. Another amino group stays free. So we have now nanodiamond terminated with reactive amino groups. Now to prove that we really form this covalent bond here, we do it by IR spectroscopy. And first of all, of course, we see signals typical for CH vibrations because we have two CH groups here attached to nanodiamond, right? So we see CH stretch vibrations here of higher intensity compared to the initial material, but it's not the convincing proof because I would say, well, if you simply physisorb this diamine on the surface of nanodiamond, you will still see these signals from CH groups. So our goal was to focus attention on the peaks characteristic for this amide bond because this bond was not present here. Okay, and we all know very well where the signals of amide group are. So those are well-known amide 1, amide 2 bands in IR spectroscopy. So we focused on this range of the wave numbers, and you can clearly see that these amide 1 and 2 vibrations now appear here as small peak here and another peak here, and these peaks are not present in our carboxylated nanodiamond. So now this tells us that we form covalent bonds between nanodiamond and this diamine, okay? And of course, since we have now amino group on the surface, and here we had carboxyl group, and you know that carboxyl group is acidic, amino group is basic group, so we expect different behavior when we titrate these materials at different pH. And this is exactly what we see. Zeta potential and size behave totally different for carboxylated material and aminated material when we change pH. So carboxylated material, for example, becomes much better dispersed in basic pH because these groups dissociate in basic pH and we have negative charge surface. And then since all nanodiamond particles have same charge, negative charge, they repel each other and stay dispersed. Aminated material becomes better dispersed at acidic pH, sorry. And again, it's in agreement with its basic character because amino groups get protonated when we shift pH to basic range, and now we have NH3 plus on the surface, so all diamonds have positive charge and they again repel each other and stay well dispersed. Fine, so what we can do with this material, with aminated nanodiamond? You probably all know that epoxy glues, when you go to a variety store and buy epoxy glue, it normally comes into two vials, right? One has epoxy resin, which has chemical structure, and another has so-called curing agent. Curing agent is normally molecular amine, polyamine, and the reaction when you basically mix the two. The reaction happens between amino groups of the curing agent and epoxy groups of the resin, and you form a solid body. So it cross-links epoxy resin and you form a solid body. So this is how the traditional epoxy system works. So we thought that we can now replace the curing agent with our aminated nanodiamond, and basically also react it with epoxy resin. And in this case, what we expect is that nanodiamond will be covalently incorporated in the structure of this macromolecule. So by doing this, we actually get the best possible interface between the components of this so-called composite, because when you add nanoparticles into polymer, what you produce is a composite material, nanocomposite, right? And one of the problems in nanocomposites is that there is a very weak interface between your nanofiller, nanoparticles, and the matrix, your polymer. So when you apply mechanical load to be transferred to nanoparticles, the interface has to be very strong. Otherwise, it makes no difference. You add nanoparticles, but it makes no, it doesn't result in any improvement in mechanical properties, okay? Because the load cannot be transferred to those particles. So in this case, we solve this problem because we produce the strongest possible interface between polymer and nanodiamond. We produce covalent bonds, and there is nothing stronger than that. I mean, what is stronger than covalent bonds? Probably nuclear interactions, but we don't know how to manipulate them. So covalent bonds is the strongest interface we can make. And this is what we do by mixing aminated nanodiamond with epoxy. So this is a molecular model of what we expect to achieve. And now let us see what we got in the experiment. So first of all, we know that we have covalent bonds between amino groups and nanodiamond surface. I showed you on the previous slide, we proved it with IR spectroscopy. Now, how we can monitor the reaction of amino groups on nanodiamond with epoxy resin? We can do it by using differential scanning calorimetry. Differential scanning calorimetry shows you heat evolved during the reaction. So when we mix nanodiamond with epoxy, and if there is a reaction, we expect to see heat evolved, and we can measure that heat. And in DSC experiment, the amount of heat corresponds to the area of these peaks, which are shown here. So this is what we are after. And we do this experiment with two different kinds of nanodiamond. Well, first of all, we check pure epoxy with no nanodiamond. We heat it within this temperature range. Nothing happens, okay? So there is no heat evolved. There is a small step which corresponds to glass transition, but it's not due to chemical reaction. And this is expected because epoxy should not react with itself within this temperature range. Then we add COH terminated nanodiamond, which is shown by green dots here, and also heat it within the same temperature range, and again, no reaction, no peak, no heat. Then we mix aminated nanodiamond, and you see we immediately start seeing the peaks, and the amount of heat evolved is proportional to the amount of nanodiamond added. So we can even measure the content of amino groups which reacted in this reaction, knowing the heat of reaction of one single amino group with epoxy group. Okay, and by doing this, we estimated the amount of amino groups on our aminated nanodiamond, and it turned out that we basically terminated about 25% of surface atoms in nanodiamond particle. So it reacts with epoxy, and we form these covalent bonds, and how it translates into mechanical properties is shown here. This is non-indentation experiment, and the parameters extracted from this non-indentation experiment are listed in the table, and you can see that Young's modulus improves upon addition of 7% of aminated nanodiamond, while compared to epoxy, the improvement is about like 10 times or so. Compared to carboxylated nanodiamond, it's still 1.5 times improvement in Young's modulus. But then if you look at hardness, for example, the improvement in hardness is 300%. So it's 3 times improvement compared to non-aminated material. And when aminated nanodiamond works even better when you double the concentration of non-aminated material. So if you use 14% of carboxylated nanodiamond, you are still way below the hardness achieved with aminated material. And we also reduce creep. So these are indications of what we can achieve by designing nanodiamond for this particular application, and by then covalently incorporating this nanodiamond into the structure of composite. Okay, so of course these composites show very high mechanical properties in other tests. For example, the epoxy nanodiamond composite can scratch the surface of alumina, which is a very hard material. Can you imagine polymer? Epoxy is polymer, right? So polymer with nanodiamond scratches the surface of alumina, which is very hard. It also has very low friction coefficient, is shown here. So this is for 33 volume percent of aminated nanodiamond. The friction coefficient is the lowest compared to all other materials. This is neat epoxy, other different nanodiamonds in different amounts. So basically when you covalently incorporate high concentration of nanodiamond into epoxy, you achieve very low friction coefficient. So the applications for this material come to your mind immediately. This composite, nanodiamond epoxy composite, is somewhere here in this diagram, which shows the different materials plotted in terms of their function of their Young's modulus as a function of hardness. And you see that typically polymers are very much to the left compared to our material. So our nanodiamond polymer composite is close to glasses, close to metals and alloys, okay? It has very high mechanical properties. So any applications where you use metals, alloy, glasses, you can potentially use this composite. For example, some of them are shown here. You can make bores for oil drilling and so on. And in particular, we did try to use nanodiamond to improve properties of biodegradable polymers, and this work was covered by Chemistry World in 2010. I like the title they gave to this work, Nanodiamond Encrusted Bonds. I think that attracted attention of people. But in reality, yes, you can improve properties of biodegradable composites, bringing them to the properties of bonds, okay? You can also use nanodiamond for many other applications. For example, for drug delivery. And again, it was shown many times that it works for drug delivery. It works perfectly. Nanodiamond, by the way, is biocompatible. This material is around us for more than 50 years. And there are no papers indicating that this material would have any cytotoxicity or other harmful effects on cells. And that is what attracts attention of people working in drug delivery to this material. But again, you need to be very careful about surface chemistry. So my main message, which I'm trying to deliver with my work, is that you need to always pay attention to characterization, modification, and rational design of this material. For example, I show here the difference in drug loading for two different nanodiamonds. This is aminated nanodiamond, this is carboxylated nanodiamond. And here we use the drug which is called polymyxin B, which is an antibiotic used to kill gram-positive bacteria. And you can see that depending on surface chemistry, the loading, this is simply adsorption isotherms. But this is how you load your drug on nanodiamond, by adsorption. The loading capacity for aminated material is almost twice less compared to carboxylated material. Of course, if you want to implement this material in any clinical environment, you have to pay attention to things like this. And in this particular case, it was easy to explain because carboxylated nanodiamond has, again, negatively charged carboxy groups when you place it in water environment. And this is polymyxin B, which has a lot of NH3 plus groups. So there is electrostatic attraction between nanodiamond and this molecule. This is why you have higher adsorption capacity. In case of aminated nanodiamond, now you have some amount of amino groups on the surface, and then they repel positively charged polymyxin B. So you have less adsorption capacity. So again, one has to pay attention not to only toxicity or non-toxicity of this material. One has to pay attention also to other properties, such as surface chemistry, for example. We can also make this material fluorescent by attaching long chain amines to the surface of nanodiamond. This is how we do it. And of course, since this material has long hydrocarbon chains on nanodiamond surface, it behaves as strongly hydrophobic material. Okay, compare this to this. This is hydrophilic. It has carboxylic groups. So when you disperse this hydrophilic material in toluene, which is shown here, it precipitates immediately. It doesn't like toluene. Toluene is a hydrophobic solvent. This is hydrophilic material, so it doesn't disperse well. When you attach this long hydrocarbon chain, it disperses much better. So this is ND-ODA, and ODA stays for octadecyl amine. So this is this molecule here. So it's very hydrophobic. But this is what we expected when we started this work. What was totally unexpected to us, that this material, in addition, demonstrates very strong fluorescence, which is shown here. So here is pure solvent, which is chloroform in this case, and I try to disperse in DCOH in chloroform. It doesn't like it, it doesn't disperse. You can see it sticks to the walls, it forms agglomerates in solution. You will see particles there if you look closer. So it doesn't like it, it doesn't disperse, and it shows no fluorescence. Now our ND-ODA material disperses well. Okay, so this is lower concentration, this is higher concentration. It disperses well. When you put it under UV light, you will see very strong blue fluorescence. And again, you don't need even any tools to detect it. You will see it with your naked eye. Okay, so now this is still another puzzle. Why this material is fluorescent? Because nanodiamond and DCOH is not fluorescent, and you can see it here, no fluorescence. Octadiethylamine, chemists know that this molecule is not fluorescent, right? So when you combine two non-fluorescent things, you suddenly produce strongly fluorescing material. So I still don't know why it has this strong fluorescence. There are some hypotheses, but still no satisfactory explanation. But anyway, this experiment was reproduced since 2009 by many groups, many times. So yes, it's strongly fluorescent. The question is still open, why? But even without knowing how it works, we can start using it, for example, for bioimaging, and this is what we are working now in my group. We already demonstrated that if you put it in contact with cells, NDODA accumulates in cytoplasm, and here you see this green confocal microscope image here. This comes from NDODA. When we stain the nuclei of the cells, we can clearly see that nanodiamond does not accumulate in the nuclei. Okay, so this is where the nuclei is, and we can prove it by using specific staining agent for the nucleus. Okay, and nanodiamond stays in cytoplasm. So this opens up additional opportunities for this nanodiamond to be used for biomedical imaging. And finally, let me say a few words about MXenes. So now I'm going from 0D to 2D materials, and few years ago, we all knew that graphene is 2D material, right? This is what Nobel Prize was given for in 2011 for discovery of graphene. So probably still now this is the most known 2D materials. But what we have besides graphene? Well, it turns out that not that much. We have hexagonal boron nitride. We have transition metal dechalcogenides, for example, molybdenum disulfide. We also have transition metal oxides and hydroxides, clays. Is there anything else? Well, in 2011, at Drexel University, it was shown that yes, actually you can produce many transition metal carbides in 2D form, and those were called MXenes. Now, when I teach my students about MXenes, this is what I usually mention. Look at this structure. This is the structure of graphite. If you look at this structure, you immediately see that it's made of layers of carbon, right? So this structure just invites you, try to exfoliate it, try to separate those layers, because there are no covalent bonds between the layers, only weak van der Waals bonds. And this is what many chemists were working on. And surprisingly, this seemingly simple problem took around 150 years to solve. And again, was culminated in Nobel Prize in 2010. And eventually it was done by simply using Scotch tape, as we all know now. But people were working on it for more than 100 years, and they tried all possible sophisticated techniques. And remember, there are no strong interactions between the layers. Now, what would you say if I would come to you and show you this structure, which is titanium carbide? You cannot clearly even see layers here, separated layers, right? Everything is connected by strong covalent bonds, and those bonds, TIC bonds, are some of the strongest bonds in nature. So if I would tell you, okay, now do same with titanium carbide. So basically, separated titanium carbide into 2D layers of titanium carbide. What do you think? How long that would take? Well, we know this took 150 years. This would probably take forever. And that would be probably the most normal answer in this situation. So again, what I'm saying, why I'm calling MXenes extreme materials, because what we're talking about are 2D forms of extremely hard materials, extremely strong bonding here, and extremely large number of new 2D materials. And let me tell you this problem, seemingly very difficult problem to solve, was solved at Drexel by a PhD student, Mike Naguib, who is a very good student. He is now at Oak Ridge National Lab, a postdoc at Oak Ridge National Lab, so he was a good student. And it was solved within, I cannot tell you exactly, but it was like 2-3 years, okay? So how it was done? You may be surprised. How it was done? Well, of course, Mike is a very smart student, so he did not solve it. He did not try to break the bonds in titanium carbide structure. So the key for this solution was the choice of initial materials. Okay, so we want to produce 2D transition metal carbides, but we start not with bulk transition metal carbides. Instead, we start with materials which are called max phases. What is max phase? Well, max phase is a layered hexagonal material which is formed of blocks of MX with A element layers shown in blue here between these blocks. Now, what is MX? M stands for early transition metal, which can be any of these red elements here. X stands for carbon or nitrogen, okay? And A element, which forms layers between the MX blocks, is any of these elements. So most common max phases have aluminum as A element. And then these MX blocks can be of different thickness. So they can be of 3 atomic layer thickness, where we have M element layer, X element layer here shown in gray, and another M element layer. So 3 atomic layers thickness. They can be 5 atomic layer thickness, where we have M element, X element, M element, X element, and M element. So this is our MX blocks. And then A element layer. Or they can be 7 atomic layer thickness, okay? So you already start to get feeling that the amount of these max phases is quite large, right? So they differ in terms of M elements, A elements, they differ in terms of the thickness of these MX phases, and the number of max phases right now is more than 70, okay? Now, what we do with those max phases to produce Maxine? So here is an example. We take one of those max phases, which is titanium-3 aluminum C2. This one has MX blocks of 5 atomic layer thickness. So it's M, X, M, X, M, right? And here's the layer of aluminum, A element, okay? So we take this max phase. Max phases are well known. We did not discover them. So we took them and treated them with HF. When we treat them with HF, what we do, we basically remove aluminum, A element layer. And what we end up with are just MX layers. This is what gives the name to this material, Maxine. So we start with max phases, we cross the A because we remove it, we have MX, and then to emphasize that this is a 2D material, we basically add the ending in. So the name is Maxine. Okay, in analogy to graphite. Now, since we do this reaction in aqueous environment, it's aqueous solution of HF, the surface of Maxine layers is terminated by OH groups. So this is OH, this is oxygen, hydrogen, oxygen, hydrogen. And then if we take this structure and sonicate it, we have separate layers of Maxines in solution. So this is how first Maxine was born. And again, this is Mike Naguib, first author of this paper, published in 2011. So that was the first Maxine paper. Now, this was just one example of max phase, okay? You can imagine, let me skip this slide, not that important. You can imagine the potential number of Maxines, of different Maxines. So we have more than 70 max phases. Potentially, if each of those max phases can be exfoliated and produce Maxine, so the number of Maxines becomes huge. It's actually the largest family of 2D materials known now. So this is the number of potential Maxines which can be produced. Okay. Now, what we have produced so far is not that much. We actually produced Maxines only with these elements as M elements. And we produced mixed Maxines where we have solid solutions in M sites. So it can be titanium niobium carbide, for example, titanium vanadium or vanadium chromium carbide. which adds chromium also to the to M elements. But in terms of A elements, so far we were able to work with only aluminum max phases, okay? So there is still a lot of work to be done for MXenes, and you can imagine how large is this family. Now, to
So,
show you...
Dr. Mochalin?
Yes, yes.
Yeah, we need to end now because we are at the time 5:30. Yeah,
Fine.
yeah. So if you could wrap up in like 30
I will wrap up.
seconds.
Sure. Okay.
Thank you.
So basically, let me skip all this because I can talk about MXenes for hours. Again, the number of MXenes is large, the applications are many, and a lot of work has to be done. Let me just jump to conclusions. And to conclude, I just want to tell you that nanomaterials hold huge and still underexplored potential to change our lives. For example, nanodiamond can be used to deliver drugs. It can be used for biomedical imaging, to produce advanced composites and many other things. You just need to pay attention to its surface chemistry. You need to design this material for each particular application. You cannot simply take random nanodiamond, random polymers and mix them. MXenes is a unique, large family, potentially the largest ever family of 2D materials. So we still know very little about MXenes, I would say less than 10%. There's a lot of work to be done. Very little is known, but what we know so far is actually what gives us inspiration to continue to work on this material. Because even what we know so far is so exciting and points out to so many different opportunities that we are very excited to work on this family of 2D materials. Thank you.
Okay, thank you very much. Probably one question. Okay, we'll take one question. Okay, there are lots of hands, so we'll try to get through as many questions as possible before we lose our audience.
Okay.
Hi, my name's Emily. You talked about how the MXenes are all like incredibly strong. How does their strength compare with like the strength of a diamond? Just
Okay. Well, I think it's not fair to compare strength of a diamond to strength of MXenes, because one is 0D material, another is 2D material, and again, dimensionality changes mechanical properties as well. But I can compare MXenes to graphene. Okay, graphene has, for example, Young's modulus at around 1 terapascal. MXenes have Young's modulus at around 5 to 600 gigapascal. So it's twice less strong in terms of Young's modulus compared to graphene. But if you compare other mechanical properties, for example, bending rigidity is much stronger for MXene compared to graphene, because graphene is just one atomic layer thick, so it's very flexible. MXene is at least 3 atomic layers thick. And that is very important when you design, for example, sensors, when you design resonators. Then this property of MXene is very important, and in that respect, it's much better than graphene.
Hi, my name is Gabriel. I was wondering, is it possible to synthesize bulk diamond by detonation?
Not yet. The reason is the process is very short. So particles have no time to grow to anything larger than 5 nanometer. Unfortunately, not yet.
Hi, I'm Adriana, and I was wondering if possible, like, are there any kinds of other nanoparticles and materials that you can synthesize via detonation synthesis?
Oh yes, yes. It's actually a very large area in material science, detonation synthesis of materials. You can synthesize different ceramics like zirconium carbide, boron carbide. You can sinter materials. So yes, the range of materials is large.
Hello, my name's Noah, and I was wondering if you did performed Raman spectroscopy on the functionalized nanoparticles, the functionalized nano diamonds.
I did, yes. We did, and actually one of the papers we published back in 2010, I believe, was exactly on this, on contribution of functional groups into Raman spectrum of nanodiamond. And it turns out that they do contribute. For example, OH groups, they contribute into Raman intensity at around 1640 to 1680, which was before that paper was basically explained as graphitic carbon and other defects in nanodiamonds. So we were the first to show that that contribution comes mainly from functional groups, from OH groups on nanodiamond. Yes.
Thank you very much. Very interesting seminar. We'll look it up online some more too, but we've lost our audience pretty much.
Okay.
But thank you very much again for a wonderful presentation.
You're welcome. Thank you too.